All right, hello. Thank you for waiting for me all day. So I'm Kwan. I work at UrbanFootprint, and the point of this presentation is to talk about how we compute walk and transit accessibility in UrbanFootprint. And I don't actually just want to talk about how we do it at UrbanFootprint, but I want to give everybody here a set of open source tools and frameworks that are really quick and handy, so you can do this on your own if you'd like to, or you can use UrbanFootprint for the enhanced features. So before I start, what is accessibility? Accessibility is the measure of the capacity of a location to be reached by or to reach at different locations. So it's not coverage per se in a spatial sense. It's actually given a target set of resources or a target set of point of interest, how many of those in relation to the total available points of interest can I reach in the most efficient measure, and that's measured by time in our case. And so how does that relate to UrbanFootprint? UrbanFootprint is a scenario modeling platform for urban planners or other individuals in this realm. And what you can do is you can draw different types of land use or transit futures, and you can compare the performance of the two. And you do that with our national parcel canvas layer, which includes a bunch of metadata at a very fine grain. So there's parcel level accurate residential employment mix, building typology, built form, and land use types. And then you're able to compare the different types of scenarios that you paint for these different futures through either summary statistics or, in our case, we also offer a suite of modules to perform, for example, greenhouse gas emissions, household costs, fiscal, induced vehicle miles traveled, trip generation, public health, et cetera. And all of these modules utilize our accessibility module at its core. Your ability to access resources defines the agent's behavior on the network, and that's critical for changing, for example, mode choice or travel patterns in an area. So what you see here on the left is the East Bay in California, and we have Berkeley, Oakland, down to Alameda, and we've done a parcel level accessibility analysis of employment. And that type of information allows our modules to indicate whether the type of travel pattern is like transit or vehicle. And it also induces different types of like greenhouse gas emissions or fiscal consequences. So there are two primary, at a high level, elements of transit accessibility. There is the walk network, and then there's the transit network. And the walk network comes from OpenStreetMap, and then the transit network we utilize is based off of GTFS, General Transit Feed Specification. And it's basically a format for holding schedule information by a transit operator over a given set area. And it's a non-spatial or an aspatial data set. And what we need to do is take these two and convert them into a network graph. And if you're here, you probably know what a network graph is, but just in case, it's a set of nodes and edges, and the nodes are points of interest, and the edges, or in OSM, the ways, are the components that connect any two set of node pairs. So for example, if we were to walk outside out front, you might imagine that two intersections are connected by an edge, which is the sidewalk, and we have metadata about that. For example, the incline, the type of sidewalk that's there, and the distance. And we use that information to compute a cost to connect from one node to another. And you see graphs, these are graphs, and you see them every day. For example, here's a transit network. This is the London Tube, and it's also a graph. And in OSM's example, here's a city in Italy, and also Cambridge in Boston. And both of those are graphs. Everything is a graph. So it's awesome. So we have, first let's gather the walk network data as a first step for computing this accessibility. And there's two quick ways if you would like to do it in like a Jupyter notebook, for example, that make it really easy to do this. And the first one utilizes OSM's Overpass API, which allows for very complicated queries to be set against a fairly fresh, updated snapshot of the OSM planet. But there's a utility called OSMNX, which is a Python library, and it actually obfuscates all of that. And you can literally type in, for example, Manhattan, Columbus, Ohio, and you can just ask for the type of network, drive, walk, and it'll actually generate and produce that and instantiate a graph for you. And that, as you can see, it's like one line. Another option that's being discussed at this event that's really fast and handy is the shared streets protocol. And the shared streets protocol has a Python library that interfaces with the shared streets API, which again is quite simple. You pip install shared streets, and then you simply request the tile that you are interested in. So in this example, you can actually see this is the shared streets output. So you can see the tiles, as you can see the grid, kind of along the edge of the network that's rendered there. And this is the walk network for the East Bay and parts of San Francisco and the peninsula. And then you need the transit network. So in this example, again, I have the transit network overlaid there. And the transit network is produced from that GTFS data that I was discussing earlier. And there are two primary aggregators of GTFS data. There's transit land and transit feeds. And both of them have helpful blogs about how to pull down their data, but it's basically a zip file of text documents. And once you pull that down, there's a handy tool, caveat, I wrote it, but it's called Pear Tree. And again, I'm trying to show that these are just very quick one-liners. With Pear Tree, you can simply request a representative feed from the total operator schedule, and that feed will produce to you, so for example, in representative feed, it'll produce to you the typical schedule. It'll analyze all the schedules for all days produced by that operator and give you a typical schedule back. And then from that, you simply need to indicate the parameters for the time that you're interested in. So in this example, I say load feed is graph, and I have a start and end time, which is the peak hour for the Bay Area, so 7 to 10 a.m. And I say from the hours of 7 to 10 a.m., please produce a graph for me that is representative of the bus performance during that time period for every single route and every single stop pair in that schedule. Once you do that, just like with OSMX, it's easy to just plot and visualize and sanity check your outputs. So here's a quick example. I quickly unzipped the MTA's Brooklyn GTFS feed, and I rendered it here. And as you can see, it makes it spatially correlate with the locations of the stops, and you can then actually observe any of those edges and see what the runtime performance is for any edge between two stop sets. Now we just need to get that and the walk network stacked together. Unfortunately, we can also, at this point, now that we have these two components, we're actually not just limited to those two components. We can actually synthetically add any additional routes that we're interested in. Let's say we want to add a new bike lane to a part of the city. Let's say we want to add a new BRT lane or a new bus route or a new train line or even a new bridge. It's quite simple to do that by simply using a custom formatted GeoJSON that has a few key parameters, and you can simply stack that on top of the network as well. And that's what's really nice here in Pear Tree is that once you pull in one feed, you can actually continue to instantiate additional feeds and simply provide in the existing graph. It'll connect all the existing components together and continue to stack your graph as many times as you want with any types of mode combination that you're interested in. So once you have that instantiated graph, again, I'm trying to emphasize these one-liners here. Here you can just do an ego graph, which is essentially the computation of an isochrone on that network graph with network X, and it's actually pretty fast, pretty simple. Again, you could do this all in a few lines in a Jupyter notebook. And here, if it might not be visible, but in green, in the center is your walk network, and in pink outside is the transit network. So you can see the difference in your walk shed within 20 minutes and your transit shed. And again, with 40 minutes, and you can see most of the East Bay. So isochrones are pretty popular in the past few years. Mapbox has set up an API. Mapzen, rest in peace, had a mobility tool that produced isochrones as well. And then Conveil Analysis has a really detailed isochrone analytics platform called Analyst. Anyway, so those are awesome, and they're also really fast to compute. The challenge at UrbanFootprint is that we don't want just one isochrone. If somebody's doing a large project, you might want hundreds of thousands of isochrones computed at once, and you want the results for all of them. Because what you want is not the performance of a single parcel in a region, you want the performance of all parcels relative to all other parcels in the region. So here what you have is a chloropleth of all parcels in Oakland and their proximity to the nearest school. And what you want is not how far away a given parcel is from a given school. You want to know how far away relative to all other parcels a given parcel is from a given school. And then, for example, for something like parks or complex geometries, not points of interest, we need to disaggregate those using, for example here, Delaunay triangulation, but basically we need to break up large points of interest or large geometries into a subset of shapes and then apply that subset of park acreage to the nearest node. So, for example, if you want to calculate how much park acreage you can reach relative to all other parcels, you need to have a disaggregated shape here. So again, computing this just in NetworkX and just in Python, just in your notebook is actually quite simple. So if you were to run the ego graph over all nodes in the network, and again, this is that walk AC stacked, you can actually see what we have here is just the number of nodes. So every node has a value of 1. And you're saying, how much of the rest of the network can I reach? And you can see the fade off of the network here in both of those images. But one of the disadvantages here is that once you're reaching the hundreds of thousands of iterations, there are performance hits. This could take hours to run, unfortunately. So there are a few things that you could do to help speed this up. You could simplify the graph, for example. You can remove all intermediate nodes and just take the intersection nodes, and you could just drop all the complexity there and say, this is roughly close enough. I'm happy with a block level analysis, and that's what we've done here in this example. And again, when you're looking at a region level analysis, that's actually acceptable. This is, again, the same thing run, much faster, and as you can see, you still capture a lot of detail. This is as you can see, these white lines are the impacts of freeways and large roads on the accessibility of different regions. And then another thing you can do is if you know that you're working at a larger scale, you can use a coalesce operation. And again, these are just one-liners, so this is just PT coalesce. You run coalesce and you set a meter resolution. So in this case, I set 400, which is roughly a quarter-mile resolution. And you can take the fairly complicated network of, say, AC transit or a walk network, and you can reduce it to a handful of nodes, on the order of hundreds, if not from tens of thousands or hundreds of thousands. And this makes all these computations fairly trivial at this point. Those are all awesome, and they do help with analysis for small sites. But what if you want to get bigger? And that's what's happened at UrbanFootprint. We have customers doing the entirety of, for example, Central Ohio. So this is a customer doing the 7-county region around Columbus, and they wanted to compute accessibility to every parcel or every single geometry within this project area. So at this scale, you're still hitting performance walls. So there needs to be further improvements. So if you've reached this point and you still want to keep going, there are options. There are 3 options. There are 3 options for Python specifically. There is GraphTool, Pandana, and iGraph. And all of them are essentially Python wrappers over C libraries that assist in utilizing common graph algorithms. The iGraph and GraphTool are more general use, and Pandana is actually specifically for doing all-to-all calculations. GraphTool I prefer the most because it is stable and it's essentially a wrapper over Boost, which is a set of C++ libraries that are well vetted and performant. So once you have, again, just trying to emphasize that these are all one-liners, you can simply say, from pair tree, import NetworkX to GraphTool. And in one line, you can convert and instantiate the NetworkX graph at full resolution in GraphTool. And once you do this, you have the entire network held in C instead of in Python objects. And computing any sort of calculation becomes much faster, like from seconds for each operation to milliseconds. So again, here I'm just showing that we're looking at the same graph again. This is the AC transit system. I didn't do the walk network because I was just doing this quickly earlier. But one thing that you can do that was fairly complicated in NetworkX before is this is betweenness centrality. So betweenness centrality is the calculation of the shortest path from all nodes to all nodes. This type of operation in NetworkX can actually take, on a medium-sized graph, can take dozens of hours. And once you're doing this in GraphTool, it's on the order of seconds at most. And then what you've computed here is you've contorted the graph and you've actually identified the core segments of the transit network, and this actually allows you to observe what components or what segments of your transit network are the most important and the most critical. So what are actually your points of failure? If these components of the network become distorted or not performant in any way, your entire network falls apart. So again, GraphTool is quite simple, and actually I'm going to show breadth first search. Dijkstra would actually be the best algorithm to use for the type of analysis we're doing, but this one just shows you how simple GraphTool is. We simply, if we want to perform the same sort of all-to-all analysis, we simply instantiate this visitor object, which defines what GraphTool, a set of instructions for GraphTool to execute as it moves through, as it performs an algorithm, like such as breadth first search, and moves through the network. And simply, so in this example, I'm just saying, please just calculate your current distance, the current amount that you've traversed, and also return to me the value. So you could imagine if every node had the number of households or the number of employment, it would also say, by the way, you've reached this distance and you've now reached this many households, this much employment of this type, and you've accessed X number of park acres. And then it's just a matter of running that in parallel on all points, and you're able to compute all-to-all accessibility in under a second, or very trivial amounts of time. And again, this is the output in both ways for the AC transit system. And then here's seeing, how you could actually use that in UrbanFootprint to kind of bring it all back to UrbanFootprint. So here, this is it from a blog post, and what we're doing is saying, in St. Louis and Detroit as well, there's a large amount of vacant housing stock, and it's very hard to decide which ones to deal with first. So what we did is compute transit accessibility and say which households, which units, if you renovate them, have the ability to increase access to transit to employment and certain types of employment the most. And that's basically what we're doing through a quick selection from the accessibility output. Anyway, hope that made sense. And that's all. Thanks. Okay. Yeah.
Do any of the graphs have any rating like traffic or population data now?
Yes. Although right now we don't do. Once we get a hold of good traffic data, you could do this for auto as well. That's just mostly a data question. I think Conveil is awesome at stress testing your transit network. This might be more from the perspective of a planner or a land use planner or a developer or somebody that's not focused on transit optimization. What I think is awesome that Conveil does is they can actually stress test your GTFS and say, look, you claim you have this level of coverage, but if a person leaves a minute later from their home, they actually can only access a significant subset of that target area, which means that you have a very fragile transit network. And you can't really do that here. So that's, I think, a different perspective.
Okay. Now, I was looking for what are the advantages of the method you're using?
I think we're doing something fairly similar. We're just doing it at a parcel level because we want the performance of a given parcel, whereas Conveil is just gridding up the entire world into, I think, a 200-meter grid. I can't remember off the top of my head. But they just grid up the world, and then you get something that looks like a raster output. Awesome. I'll also post this somewhere online afterwards, but it's basically OSM and X, shared streets, pear tree, and then network X. And then if you want the performance, GraphTool.
I think you mentioned briefly about defining where the most critical components of your transit network are.
Yeah.
What is that? How can you
So does anybody follow Elon Levy at all? One person. Okay. I can show you an example. So he's this, I think, is he a crazy French guy? I'm not sure exactly. But he basically proposed a complete redevelopment of the MTA Brooklyn system, and he was observing a lot of the fact that there was like huge performance hits on certain components of the network. And you can actually see that if you run a between a centrality analysis on the MTA system in Brooklyn. What you see there is the current system, and you can actually see Flatbush. You can see the big red swath. That means all of the buses are getting routed along one core route. So if anything happens on Flatbush, which happens about every 20 seconds, your buses start bunching. And when your buses bunch, they bunch all throughout the day, and starting from the early morning, your entire system is screwed for the rest of the day. And MTA has serious performance issues related to this. What Elon Levy did was he tried to distribute the performant bus lines and lower the number of routes and increase the frequency of buses along those routes to reduce risk of this sort of like single point of failure. And then I ran it between us in centrality on his proposal as well. And you can see a much more balanced network with higher levels of accessibility throughout the network. So what happens here is, let's say something happened on Flatbush. You're actually okay. You can actually get all around Brooklyn still. All the other buses are still running frequently and have high levels of accessibility. All right.